All right, guys, let's go ahead and go over the warm-up question for today so that we can get into our notes. So again, if you are chatting, I'm going to ask for you to quiet down because we're going to be taking notes today on circular motion calculations specifically. I did give you the equations yesterday, so maybe you tried out some of those calculations. Maybe you found them easy, maybe you didn't. We're about to go over those today. And then you will be finishing up the assignment that you started yesterday, 801.2. That is due by 11:59 p.m. tonight. And the other thing that you can be looking at as you prepare for your test, which is in 2 days, is the unit summary that is now posted to Schoology. So you do have that as well with some additional practice. All right, so let's go ahead and take a look at the warm-up question, and this is something that was in yesterday's notes. It says, if you are sitting in the back seat of a car that makes a hard left turn, you will feel pushed toward the right side of the car. Why does your body move to the right? And we talked about this because it is part of a misconception that people have. Oftentimes students think that there's some kind of force pushing objects out of circles, out of circular motion. Okay, but that's not the case. Whenever we looked at this yesterday, we looked at this example because in this example, this car turns and this child falls out in the middle of the intersection. Okay, and we talked about how an object in motion will remain in motion with a constant velocity, and that means in a straight line at a constant speed until some external force acts on it. In the case of this person in the car, and that's why I have this image here, the car is moving toward the top of my screen. The person is also moving toward the top of my screen because they're in the car. But when the car's tires turn, and there's that friction between the tires and the roadway, the car's going to turn, but you're not touching the road. You're still trying to move toward the top of my screen. And whenever that happens, especially if this happens really quickly, if you're trying to move toward the top of my screen while the car is now trying to move toward the left of my screen, you're going to feel pushed toward the right, which is what you would see if you look at the direction this guy would feel pushed, is up toward the top of my screen or to his right from his perspective. Okay, but again, that's not a force pushing him. Rather, it is his inertia. Okay, so because he is an object in motion, he wants to remain in motion with a constant velocity. That's his inertia. It feels like he's being pushed outward, but it's just the fact that he was already going that way. It's the car that's changing motion, and he wants to keep going the same way that he was going, and he'll stop because of the friction between him and the seat, or maybe the seat belt, or if it's a really hard turn, it might even be the door of the car, but there hopefully is something that's going to cause them to turn. Now, if the door's open and there's no seat belt, then you have this, where this kid falls out into the roadway. And so that could happen if you don't have that force to keep you in circular motion with the car. But anyway, there is no force pushing outward. We talked about this yesterday. There's even a name that people give that feeling of being pushed outward, and they call it a centrifugal force, which can be confusing because it's not actually a force. Okay, and I told you to remember F is for fake, because centrifugal and centripetal sound pretty similar, but the one with the F in it, centrifugal, that's not a real force, it's fake. It is the result of your inertia. So again, please make sure you have your warm-up question answered in My Open Math. And as I said, we are going to be getting into some notes today. Before I get into the math part, I want to just really quickly recap what we talked about yesterday. So uniform circular motion is what we talked about yesterday, and it can be described as the motion of an object in a circle at a constant speed. As an object moves in a circle, it is constantly changing direction, and the change in direction means that although it's moving at a constant speed, its velocity is constantly changing. And if your velocity is constantly changing, you are accelerating. So objects in uniform circular motion travel at a constant speed, but also are experiencing acceleration, okay, because of that change in direction. And that seems contradictory, but it's not, because again, acceleration, just like velocity, is a vector. So when that direction changes, of course, you are going to have change in velocity, and thus you will have acceleration. Your acceleration is actually changing constantly too, because that one also is changing direction the entire time because you're moving in a circle. But the speed can still be constant. You can drive in a circle at a constant speed. Okay, try it on that roundabout outside the school. Just go in a circle at a constant speed. You can see it. Okay, but you would still have acceleration toward the center of that circle due to the net force toward the center of that circle. Those centripetal force and centripetal acceleration. And you can see those labeled in this diagram here. So here is how you could draw vectors for an object in uniform circular motion. If I asked you to show the direction at any given point, and this shows several of them, of course there are also points in between those, but that might be helpful for you to have something like this copied down. But you can see that the force of, in this case, tension, because this object is being swung around on a string, that force of tension is always pointing inward toward the center of the circle. And you can kind of see it behind it. There's a green arrow. I know it's kind of hard to see because it's underneath the red one, but that one's labeled with an A for acceleration. So both my centripetal force and my centripetal acceleration are inward. In this particular example, my centripetal force is force of tension because it's a string. And then you can see the velocity, that tangential velocity, that linear velocity, the way that it would go if the string were cut, and the string does get cut at the end, is labeled there by the blue vector. It's the direction that your marble went off when it left the plate the other day, that straight line speed that it has at any given instant. And of course, if you remove that centripetal force, that's the direction the object will go off in, which is what you see here at the end. There's some scissors and the string gets cut, and it gets cut right here, and this is the velocity it was going at that point, and so it just continues moving toward the bottom of my screen. Okay, but again, force and acceleration always point directly toward the center. The constant velocity points tangent to the circular path, which means it is at a 90-degree angle, a right angle to the other two vectors that you have. There is a 90-degree angle between that velocity vector and that force vector, or between that velocity vector and that acceleration vector, because again, it is a tangent to your circular path. So it will be perpendicular to the radius, which the other two are, of course, along the radius. So again, be able to draw those. And you saw it yesterday because it was in your MyOpen Math assignment. If you got stuck on those, look back at them today. All right, so why is it inward? Again, think about orbital motion. If the planet didn't pull inward on the moon, then it wouldn't be in orbit. Okay, the moon only stays in orbit around the Earth because of that constant pull inward from the Earth due to that gravitational attraction between the two. The moon's inertia causes it to want to move in a straight line at a constant speed. So at every given instant, it's got that tangential velocity, that linear velocity, and if that force wasn't there pulling it back, it would shoot off in a straight line until it interacted with something else, some other type of force. But again, it's similar with the plate that we looked at yesterday, the plate and the marble. If the plate didn't push inward on the marble wouldn't move in a circle. And we saw that as soon as it left the plate, it didn't move in a circle anymore. It went off in that straight line in the direction of its tangential velocity at the instant it left the plate. Straight line from that point. Okay, so here's something we didn't talk about yesterday, but something to think about. So this is a carousel, merry-go-round, whatever you want to call it. And they're typically, this one actually in the image has looks like 4 horses wide. But if you look at this one with the overhead view so you can see them better, it says who takes longer to complete one full rotation? Okay, so we have this green horse that's circled in red and this one's circled in blue, but which one would take longer to make one lap? Same time, right? It would take them the exact same amount of time to make one lap around it because they're fixed to the ground, right? Okay, so it's going to take them the same amount of time to make that lap. Okay, however, if you ride on the outside horse, you're going faster than the person on the inside. Anybody know why that might be? Yes, sir.
It's farther away from the center.
Because it's farther away from the center. It's a bigger circle. Okay, look at the equation. If you have a larger radius, which you would if you were on that outside horse, that's a larger radius, it's farther from the center. That means it has a larger distance to travel. That circumference is a longer distance, but if it does it in the same amount of time, you're going faster. Okay, so you're going to go faster if you're at the outside of that carousel because of that right there. Look at the equation. They take the same time, but because that radius is larger for the one farther out, it goes a greater distance. Seems kind of weird because we wouldn't think that they're traveling different speeds, but they are. The same thing, by the way, is true on Earth. If you live at the North Pole, this is what you do, and it takes you 24 hours to do it. It's very slow. Okay? Whereas if you're at the equator, you're going to have to make that entire same rotational trip, and you have a lot greater distance to travel. So the Earth actually spins faster at the equator than it does as you move toward the poles. It moves slower and slower for the same reason. The radius is larger when you're at the equator than it is at the pole, whenever you're thinking about from the axis of rotation. Okay, so again, you can think of examples like that too. All right, so let's talk about the different factors that affect the force, that centripetal force that an object experiences when it's in uniform circular motion. Again, we have this equation for it. My centripetal force equals mv squared over r, and that was the equation that I got when I took F equals ma. And I substituted my equation for centripetal acceleration, v squared over r. I substituted it in there. Okay, and so I got this. Centripetal force is mv squared over r. And so that means that these different factors, mass, velocity, and radius, all have an effect on the amount of centripetal force that an object experiences or that an object requires to remain in uniform circular motion. Okay, so let's look at these different factors one at a time. Let's first talk about mass. And I have some examples up here to kind of get you a picture in your head. It says, you may have an easy time swinging a golf ball on a string in a circle. But if you were to replace that golf ball with a cannonball or a bowling ball, something that's a lot heavier, watch out, you may now have to whip 10 kilograms around at the end of a 1 meter string every half second. You need a lot more force to do it. Just imagine trying to do it. Okay, trying to keep that thing in that circular motion. That more mass will require more force. The two are directly proportional to one another. And again, you have some of these proportional reasoning questions in your assignments. If you got stuck on them, or even if you didn't, you might still want to write down these relationships. You can see it in the formula as well. If you were to, for example, double the mass, you would therefore cause the force to be doubled as well. Okay, here's another one. Relationship between velocity and force. Imagine you're driving your car around in a circle. If you're going quite slowly around the circle, your tires have no problem generating enough frictional force to keep you going in a circle. But if you go too fast and your tires can no longer generate the necessary amount of frictional force between them and the roadway, you will skid. Again, there is a relationship between that force that's required and the velocity that you're moving in order to keep you in a circle. And again, you can see that this is a squared relationship, and I can see that because if I look up at my equation, I can see force equals mv squared over r. And so, for example, if I were to double the speed at which I'm driving, it doesn't require twice as much force now. It requires 2 squared, or 4 times the force for me to remain in that circular path because I have a squared relationship. Okay, so you should be able to see these relationships simply by looking at the equation. Okay, this one right here is in part of the training that astronauts go through because they have to make sure they can withstand the G-forces that they would experience during takeoff and things like that. They have to get inside this centrifuge that spins them really fast in order to simulate those G-forces or make them feel like there's all this force being pushing on them. Okay, and it says in a centrifuge, the faster you spin, the more your inertia throws you up against the wall, just like the amusement park rides we talked about, or the warm-up question, that hard left turn, you feel pushed toward the side. Well, this is going to do it a lot more because it's spinning a lot faster. Okay, and so it says every G is your own body weight in centripetal force. If you're feeling 5 Gs, you would feel like you weigh 5 times your normal weight. Okay, and so I'm going to show you this video clip. It's only a few seconds, or not a few seconds, a couple minutes long, but you can see these different prospective astronauts trying to train, and they're having a hard time.
All right, your first ride is going to be that gradual onset ride to a maximum of 7 Gs. Are you ready?
Yeah, ready. I'm ready.
Sure. Are you ready?
Yes. Yes, sir. I'm ready.
3, 2, 1, engage.
So you can see the forces they feel in this motion.
If you lose all the green, tell me now and start that lower body straight, okay?
Okay.
Squeeze those legs nice and tight. 1, 2, 3. You're looking real good. Squeeze everything nice and tight.
I'm moving it.
Not yet, not yet. It's only 2 G's. It's only 2 G's.
You should feel like you're going straight up in the air at this point.
That's 4 G right there. You're doing good.
3, 2, 1, engage. Back on the stick. On top, breathe. You're on top, breathe. You're on top, breathe.
Okay, big breath. Watch out for the helmet.
You're on top, breathe. Hold. On top, breathe. 1, 2, 3.
1, 2, 3. No few breaths.
1, 2, 3. 1, 2, 3. 1.
They look super comfortable, right?
Okay?
No.
Legs tight. Butt tight. Breathe. 1, 2, 3. 1, 2. Well, okay. Stay tight. Stay tight. Stay tight. Stay tight. Hello? Are you with me? Coming back around? Hello? How you doing?
What?
Hello, Bill? Bill, sit up.
I'm up.
Sit up.
I'm up.
You're up. Put your head up.
It is up.
Put your head up.
Oh.
You know what happened?
Yeah.
You ate lost.
Yeah.
What happened?
I'm thinking as you are.
All right.
Whoa.
Okay. You all right? You feel nauseated?
Yeah, a little bit. I'm gonna vomit.
Get the bag. Get the bag.
It was a big jerky.
I actually have no comments for you. Everything looks real good. How you feel? Woo! Good job.
Same. All right, but we talked about the relationship between the velocity and the force, and it was that squared relationship. So obviously you can see there's a lot more force whenever that thing starts getting faster. And a couple of them fainted. There's a lot of force here. You can see it in their face too. It looks like they're being crushed or like stuck against the wall. But it's going to feel that way, that it's hard to breathe because you feel like you have, in the case, I think they said they went up to 7 Gs. It's going to feel like 7 times the force of gravity. So your body actually feels crushed under all that weight, or at least apparent weight. But again, it spins like this. It just gets really fast. All right, so another factor will be radius. Okay, so that was velocity. But radius also affects force. You can see it in the equation. But you can see the effect of radius in your car going around in a circle. If you drive your car at a fixed speed in a circle of a smaller and smaller radius, eventually your tires won't be able to supply enough centripetal force from friction and you'll skid off your path. So again, this is an inversely proportional relationship. As this radius gets smaller and smaller, it's going to require more and more force, and vice versa. All right, so looking at this equation for centripetal acceleration now, v squared over r, what is the relationship between your centripetal acceleration and your radius? Just looking at the formula, what would that relationship be? Inversely proportional. Okay, and so if your radius were doubled, okay, how is your acceleration going to change if you have twice the radius? Half. Okay, so be able to answer questions like that. If it's 1/3 as much radius down here, it'd be 3 times. Okay, so again, those proportional reasoning questions sometimes trick you guys up, but just look at the equations. You should be able to figure it out or write it down in your notes and you can study it. All right, you also can look at the relationship between centripetal acceleration and velocity. And of course, this is a squared relationship. And so if you were to triple your velocity, for example, it wouldn't be 3 times the acceleration. It would be 3 squared, or 9 times the acceleration. Similarly, if you had half the velocity, it's not half the acceleration. It's half squared, 1/4 the amount of acceleration. So again, be able to look at those equations to see that. All right, so let's try some actual calculations. So we've just been looking at the relationships. Here is an example problem, and it might be similar to one that you could see in your My Open Math assignment if you haven't done those yet. It says, calculate the acceleration of a puck that is in uniform circular motion if the radius of its path is 3 meters and it moves at 9 meters per second. And I have a bunch of equations listed over here to the side. They're similar ones on my board. I don't have them all up there. But we're going to start just by labeling some things. I know the velocity, and I can tell that's a velocity simply by looking at the units. So if you're confused about what you're looking at, check the units. 9 meters per second, that's a velocity. Okay, I also know that I have a radius, and it says so the radius of its path is. So my radius is 3 meters. And I'm trying to determine acceleration. And so I have velocity and radius, and my formula for acceleration is v squared over r. I'm going to take that tangential velocity, that 9 meters per second, I'm going to square it, and I'm going to divide it by 3. Okay, and you can put the units in your math if you want to see which ones cancel, or you can tack them on at the end. But you do want to make sure that your radius unit matches the distance unit in your velocity. So meters and meters, that's what I want. I don't want one to be kilometers and one to be meters per second or something. So you get this. 9 squared, of course, is 81. I also square the units. But whenever I divide by 3 meters, this meters cancels one of those, and I'm left with meters per second squared. And 81 divided by 3 is 27. Okay, so I get 27 meters per second squared as the answer for this first example calculation. Does anybody have a question about this one? Should be pretty straightforward, I think. I think y'all will agree this math is easier than the last unit.
Yeah.
Nate's like, I'm not going to be shy. Yes, this is easier. All right, let's look at this one. A 0.5 kilogram ball is swung in circular motion at the end of a rope. The circular path has a radius of 0.62 meters, and the ball completes one rotation every 1.8 seconds. What is the centripetal acceleration of the ball? If I look at my equations, I know I can find centripetal acceleration if I have velocity and radius, or if I have force and mass. I can see it in both of those two equations. So looking at what I have here, I don't have those things. So what I need to do is I need to get the velocity first so that I can then use that other equation to solve for my centripetal acceleration. They did give me a radius, and they gave me a time, a period for 1 lap. So I can get the velocity, and then once I have the velocity, I can use that acceleration equation, v squared over r. So velocity is 2 pi r over period. Substituting in, that's 2 times pi times my radius is 0.62 divided by the period or the time of one rotation, so divided by 1.8. And that gives me a velocity of 2.164 meters per second. But again, this is not my answer. This is the tangential velocity. I still have to find the centripetal acceleration. But now that I have the velocity, I can do that using this equation. V squared over r will give me that acceleration that I'm looking for. So I'm going to take that answer that I just got, 2.164, I'm going to square it, and I'm going to divide it by my radius. And when I do that, I get a centripetal acceleration of 7.55 meters per second squared, or meters per second. You can write that unit either way. But that would be my centripetal acceleration based on this information in this question. Okay, second part of the question says, what is the centripetal force of the ball? Well, I have equation F equals ma. I know centripetal force equals mass times centripetal acceleration. I have the mass in the question. I just found the acceleration, so I can just plug those things in, and I can find the force. And so if I substitute those in, my mass in the question is 0.5, my acceleration that I just found is 7.55, and I get a centripetal force of 3.78 newtons. Again, these would be good examples for you to have on your paper, just in case you need to look back at them as you're trying to work through the questions on your assignment today, or maybe the unit summary. All right, last one on this screen. If the ball's mass is doubled, how does the force needed to maintain the same acceleration of the ball compare? So in other words, just look at this equation right here. If I were to double this, instead of 0.5, now it's 1, what's going to happen to my force? It's going to double, right? So we have, again, we've already looked at these relationships, but force is directly proportional to mass. Or you can go back and do it with the numbers. But because your force is directly proportional to mass, if you double the mass, you should therefore double the force. If you're not sure, double the number and see what happens. Any questions about calculations on this screen? No? We're good? All right. Heads up, this is what last year's FRQ looked like on the test. So this might be a really helpful one to write down. If I were you, I would. It says, Neptune orbits the sun at a distance of 4.5 times 10 to the 9th kilometers. If Neptune has a mass of 1.02 times 10 to the 26th kilograms, and the sun has a mass of 1.99 times 10 to the 30th kilograms, what is the centripetal acceleration of Neptune, and what is the tangential velocity of Neptune? Okay, and so first of all, you've got some numbers up here, but none of them match what I really need for my circular motion stuff. But I do very obviously see stuff I can plug into my universal law of gravitation. Okay, and the reason that I would want to use that is because that force of gravity that exists between these two, if this is the sun and this is Neptune, the force that exists between them is a centripetal force, right? You can see the orbit, that force would be inward. If I find the force of gravity using my universal law of gravitation, that force is a centripetal force, and I can then use it in my circular motion questions. Yes?
Couldn't that also equal your acceleration?
Yeah, we're going to use it to find the acceleration as well. Yeah, but we have to find the force first. Okay, so we're going to use the universal law of gravitation to get that force of gravity. That force of gravity will be my centripetal force, and then I can use my circular motion calculations. So this is what ties those two units together, is when we start talking about orbital motion. Because now we can use the universal law of gravitation to figure out our force. That force then is our centripetal force, and now we can do circular motion calculations. Okay, so again, if I label some things, I know that the distance between them is 4.5 times 10 to the 9th kilometers. I know the masses M1 and M2, they're in the question. And I know big G, it's a constant. And so I can plug into my equation, okay, however, I can't leave this in kilometers. And I've already changed it on my screen. But you can't leave your distance of separation, your radius of your orbital path. That's why it's an R, by the way, if you haven't realized this. It's because it's the radius of the orbit. Okay, that's your distance of separation. But we can't leave it in kilometers. So there are 1,000 kilometers in a meter. So if I want to convert it to meters, I simply multiply by 1,000, and this is my new value in meters. So when I substitute in, it looks like this. Okay, and again, I would recommend that you try typing this in your calculator just to make sure you still remember how to do it and that you're not making mistakes with entering it into the calculator. So I have 6.67 times 10 to the negative 11th. That's big G, that's my constant. And I have my masses 1.02 times 10 to the 26th times 1.99 times 10 to the 30th. Again, you can put those in either order. It doesn't matter. You're multiplying them. And then divided by the distance between them squared. Again, this distance in meters, 4.5 times 10 to the 12th, and that distance gets squared. Okay, if you enter this correctly in your calculator, you should get a force of gravity of 6.7 times 10 to the 20th newtons. I have the number up here on my screen in this reddish color. Okay, I'm going to give you a moment just to make sure you're getting the same thing. And then we can talk about how we can now use this to help us find acceleration. Yes?
Why did you change it to the 12th power?
because I converted from kilometers to meters. So I multiplied by 1,000. Any other questions? Okay. All right, so once you get that force, I'm going to add it down here. And this is with all the well, not all of them, but more of the digits. Okay, less rounded. Now I can find my centripetal acceleration because that force of gravity I just found is the centripetal force for the circular orbit of Neptune around the sun. That force of gravity is what keeps it in orbit, just like when we talked about the moon and Earth. Okay, and so I'm going to plug this value in for this centripetal force. I have masses. I have two masses. Which one should I use?
Neptune.
I need to use the mass of Neptune because I'm looking for the acceleration of Neptune. Okay, so make sure you don't use the sun's mass. Make sure you use Neptune's mass. So if I substitute those values in, it looks like this. 6.7 times 10 to the 20th equals, this is Neptune's mass, 1.02 times 10 to the 26th times A. I'm going to divide both sides by that 1.02 times 10 to the 26th. And I get an acceleration, and it's pretty small, of 6.55 times 10 to the negative 6th meters per second. Would be my acceleration of Neptune. Questions about this calculation? I think there was one more. I think I asked you for the velocity as well. All right, so let's do the last step then. All right, so if I want to find the velocity of Neptune, now I have its acceleration. I went ahead and added it down here to my list of information that I know. And I can find tangential velocity if I know the radius and the period, which was not given to me. Or I can use that acceleration equation. Centripetal acceleration is v squared over r, and I have those things. I have the acceleration and I have the radius. And so I can plug in my acceleration that I just found. I have 6.56 now instead of 5.5. I don't know which way it was supposed to be rounded. I had to recalculate it. But 6.56 times 10 to the negative 6th equals v squared over my distance of separation in meters. So make sure you use the one in meters. 4.5 times 10 to the 12th. Okay, so I'm going to multiply both sides by 4.5 times 10 to the 12th. And that will be equal to v squared whenever I multiply those. And then, of course, I'll have to take the square root of that very large number, 29,496,222.22 is equal to v squared. So square root, and I get this. So it's not accelerating much, but it's moving pretty fast. Okay, the velocity is 5,431 meters per second. Questions about this problem? You have one like this in your assignment if you haven't gotten to it yet. So this should help you with that one if you got stuck. Okay, and again, this is what last year's FRQ looked like, so I would strongly encourage you to look back at it. We're going to do one more of those together in our warm-up tomorrow, but you do have one in your assignment today. For the rest of the period, you should be working on that assignment, 801.2 circular motion problem set. It is due by 11:59 p.m. tonight. You guys have about 15 minutes left in class to work on it, so if you've got questions that you weren't able to figure out, hopefully you can figure them out now, work with your neighbor, or ask me for help if you're still stuck. If you are looking for extra practice and you're already done with this, use the unit summary. The unit summary is also a daily grade redo, but it is also a great review as you're preparing for your test. All right, guys, go ahead and get to it. If you have any questions, please let me know.